All right, we're going to do it. We are going to go through two things in this video. First, we're going to talk about Pearson correlations, what they are and how they work a little bit. And then we're going to switch over and we're going to talk about linear regressions. And I'm talking about them together because you always do a correlation before you do a regression. It's just how you look at your data and try to see whether or not the regression is even worth doing. That said, you may not be interested in a linear regression. You might be interested in just doing a correlation. And if that's the case, that's fine. Then just watch the first half of the video and stop it when we swap over to the linear regression. However, if you are interested in linear regression, watch the whole video because you need to be aware of what's happening with the correlations to inform your process around the linear regression. Okay, here we go. So what you want to know about your correlation. Now, first of all, I'm talking specifically about Pearson correlation here. There are other types of correlations, but we're just talking about Pearson for right now. Correlation, first of all, does not mean causation. Just because two things tend to go together does not necessarily mean that one thing caused the other. The way you can really determine whether or not cause is at play is by doing some type of experimental design. And that is not what this video is about, and that is not what a correlational analysis is about either. So just please keep that in mind. Correlations are going to measure direction and strength. So they're looking at the relationship or the association between two or more variables, and it's going to tell us how strong that relationship is and whether it's positive or negative. And positive and negative doesn't mean good and bad, right? So let's go through this a little bit. In terms of strength, we can have what we refer to as a weak, a moderate, or a strong correlation. There are different cutoff values for this depending on the community in which you work. These are very widely accepted, which is why I have them here, but always check with the people you're working with to make sure that they're appropriate. This is what I'm going to reference here. The letter we use to notate a correlation is a lowercase r. That's why you see the R here. So a weak correlation is when you get in your analysis, your software, it pumps out the numbers and the number it gives you says R is 0.20 or smaller. All right. This is going to mean that we're in that weak place, that there's a very weak relationship between the variables. When we get between a 0.20 and a 0.4, that's when we know we're in that moderate zone. And if we go beyond the 0.4, that's where we know we have a stronger relationship between things. The relationship can move in different ways. It can be positive, meaning as one thing goes up, the other thing goes up, right? As the amount of time you sleep at night increases, your test score on your exam the next day goes up. These two things go together. You can also have examples where variables are negatively related, just simply meaning they move in opposite directions, right? So the more miles you run, the fewer pounds you weigh. I don't know, silly examples here, but do you see what I'm saying? It's not positive is good and negative is bad. It just means both things are moving together, or one thing is going down while the other thing is moving up. It's just direction. The meat of the analysis, the thing we really, really love, is the thing about the strength, right? How strong is that relationship? Do they move together very systematically? This is a strong relationship, or are they really not moving together that much at all, right? It's a very weak relationship. This is what correlation tells us. Pearson correlation, I think it's the most common correlation out there. In my experience, it tells you how strongly things are associated. And here's just a very quick example for us to think about the context. So student GPA is strongly correlated with the number of days that students attend class. We will graph this information. Graphs are a very popular way to show this kind of data. As you can see on this graph, I only have a couple data points here, but the folks who have fewer days attended during the semester also tend to have the GPAs that are living in the 2.0, 2.5 zone, whereas these kiddos here who attended almost all of the classes have GPAs that are hanging around between the 3.0 to the 3.5. right? So we can see that less days of attendance, 12, 14, 16, means we have GPAs in that 2.0 to 2.5 zone. But as the days increase, 22, 24, 26, now we're moving on up here into the 3.0, 3.5. So that's showing us a relationship between these things. It doesn't necessarily mean that attendance causes GPA to go up. It could be the motivation that the students have that leads them to attend class, that leads them to do their homework, that leads them to study better, etc. So it doesn't necessarily mean the attendance is causing it. It means that it is definitely related to it. However, it's moving in tandem together. You might report a correlation to look like this as you write it out. In my video where I show you how to actually run this analysis, you'll see this kind of write-up. This is just a generic and hypothetical example of what that would look like. This is falling in the moderate range. The p-value is less than 0.05, so we would say that that was significant. Just a hypothetical example. So what does a correlation do? What's happening in the background? I'm so happy you asked me. It's really cool math. I've always thought that this was really neat stuff. If you're a math geek like me, go Google this and look at it, or find your textbook and crack it open and look at how they do this math. It is very, very cool. What you do is you calculate z-scores for everything, right? So every student's GPA gets transformed into a z-score, standardized score. Every student's attendance score gets calculated into a z-score, standardized score. And then the z-scores for GPA are all added together, and the z-scores for attendance are all added together. And then you multiply that total z-score for GPA by the total g-score for attendance, right? And this is the thing. If attendance or GPA's z-score is positive, it means that they tend to be living above the average line, because in the world of z-scores, 0 is the average. So if you transform all the GPAs into z-scores and they sum them up and you get a positive sum, right? That means they're living above the 0, that their GPAs tend to be above the average score, and it's going to be a positive sum and a positive z-score. If you do the same thing for attendance, the average z-score is always a 0. So then if you sum up the attendance z-scores that you calculated and you get a positive number, it means they're all living above the average. So in other words, the GPAs are living above average, the attendance is living above average. You multiply two positives, what do you get? A positive. They're both on the up, right? And the bigger those two numbers are, the more likely more of them are living on the same side of the line, because when you multiply them together, that product will become larger. I don't know. Go check it out if you like it. I geek out about that kind of stuff. I think it's really cool. So with that said, here we go. Just talking this through here. Here's a reference to a textbook if you'd like to check it out in straightforward statistics. But again, there's lots of other places where you could look as well. All right, how are you going to do your correlation? Well, please do your correlation with a computer. As you all know, I recommend JASP. I think that that is a great tool to use, and go and check that out. But before you do, let's swap over and let's just take a quick look at the linear regression analysis so that we can see here how this guy ties in. There are lots of different types of regressions, and what I'm talking about here today is just the linear regression, which means we're going to graph a straight line on a graph, and we're going to try to use that straight line to take whatever's on our bottom axis to predict what we have up here. So can we take the number of days students attend and predict what's happening in terms of their GPA? Right? It's the old y equals mx plus b from your math class. It's a great tool. It has lots of applications. There's so many things that we can predict. Can attendance predict GPA? Can age predict the average amount of car insurance claims? The car insurance companies would say yes. Can past credit card balance predict future balance? The credit card companies certainly hope so. If you've had a lot more on your balance in the past, they're going to be more likely to send you advertisements for new cards in the future, because past balances predict future balances. So many things, so many applications. I could go on, right? But let's just stick to the example we've been working with. This idea that we've found a moderate correlation between student attendance and GPA. Okay, great. higher GPAs are held mostly by students with higher attendance. We can do a linear regression to tell us how to predict a student's GPA based on their attendance, right? Now, why in the world would you want to do that? Well, because it gives you a formula, and that formula can help us then plan, right? We can put numbers in there and play around, and we can say, if we are trying to keep students to maintain GPAs over a 3.0, because we want to increase the number of students in our honors program, then we know we need to get them to class this many days, because when they hit this many days, that's where we see GPA go up and be predicted to be over a 3.0. It's a useful tool, right? The other thing that's really great about it is that regressions give you an R-square statistic, a capital R squared, and it's telling us how well this one individual variable, or this group of variables, if we put more than one in, can predict the outcome. You know, how important is attendance in being able to predict this? And that can be a very useful tool for us as well in our research and in our practice. If you have a significant correlation between two variables, your regression analysis will also be significant. That's just the math. That's just how it's going to work. The correlation gives you a p-value. So p's less than 0.05 are significant. Regressions will give you a p-value. P less than 0.05 will be significant. And in the regression, the test in that output that shows you whether your regression is significant comes in the form of an ANOVA, right? And then after the ANOVA, you're going to be able to say, okay, this is significant. The model is significant. Attendance can predict GPA. And then the next step is to get the equation. And so the next table down is going to give you an equation, just like y equals mx plus b, but we're going to write it in context. GPA is equal to whatever the m is, multiplied by how many days they attended, plus the b. And that table is going to give you the m, and it's going to give you the b, right? It's provided in the regression output. And then the next step you're going to do is you're going to look at the R squared, which can range from 0 to 1. And higher numbers are going to tell you that you're able to explain more variability in the outcome, right? So if you had an R square value of 0.25, and that's for attendance predicting your GPA, that means that 25% of the variability in GPA is predicted by attendance. That's huge. That's massive, right? That would be like life-changing if this is a hypothetical example. But that's the idea. You could think of it almost as like a pie of all the things that explain GPA. Of all the things that could explain why your GPA is the way it is, how much of that pie can attendance tell us and explain? If it was actually explaining a quarter of the pie, that would be a really big deal. Okay, what's happening behind regression? Again, the math is really fun. What happens is we draw a straight line through that graph. Remember that graph I showed you of the attendance and the GPA, and you'd have lots of dots all over because you would have more than 6 observations in your study. And you draw a straight line between it. The computer draws a straight line between it, where you have the least distance between the dots and the line as possible. And it finds that. And then it's going to say, okay, so we're at this point here where a student attends 15 days, right? And the line is predicting a GPA of 2.2, but we have 5 people who attended 15 days, and none of them actually have a GPA of 2.2. So let's take that 2.2 and subtract it from what we're actually observing from these students, and then we'll have these little deviation scores. And we'll do that at every single point. And then we'll try to see what is the overall deviation, right? How close are these points to the actual line? And the closer they are, the higher your R squared is going to come out, because those deviations we then use to calculate the R squared, to calculate whether or not it's significant, and get a p-value. You can find this math and really cool illustrations of it in lots of places. There's a textbook reference here for you if you'd like to do that. It's fun. If you're a math geek, check it out. Just like I said with the correlations, that just kind of gives you an idea. You know, it's really interesting, even if you're not interested in the math. Think about one of our simpler statistical tests, like a t-test. right? What are we doing in a t-test? We're taking this number and we're subtracting it from this number, and we're getting a difference, and we're trying to figure out, is that difference normal? Is it big? Is it small? What are we doing in a regression? Well, we just have to get the numbers a little different. We draw this line that fits the dots the best, and then we compare where the dot is compared to where the line is. We subtract, we're getting that difference, and then we're trying to see, is that difference really big? Is it really small? What does that mean? It's the same kind of thing. We're just looking at different scores to give us a sense of how important something is, like attendance and predicting GPA. Again, you're going to do a regression in JASP. I highly recommend that. Check out the videos that I have on how to do that, and get JASP and open it up and start running correlations and start doing your regressions, and have a great time doing it.